How we doing, folks? Today we're going to look at simple harmonic motion. More specifically, I'm going to solve three problems dealing with horizontal spring systems. We'll start with a single spring attached to a block. I'll then add a couple single springs, either in parallel or in series, and I want to compare the differences to the first case. I also want to say a few things about a vertical spring mass system. There are a couple important differences I want to highlight and just make sure you understand the differences. So in all of these cases, really what I'm interested in is the angular frequency omega, which I write as omega, and I'm also going to be interested in calculating the frequency or the period of oscillation for all of the different cases. So let's get started. Okay, so here's a sketch of the three different cases I want to look at for the horizontal spring and mass system. The first is the simplest. We have a single spring that's connected to a block of mass m. The spring is characterized with a constant given with the letter k. In the second figure over here, I have two of these simple springs that are connected in parallel to one another. The most general case, the springs can be different or have different spring constants. And in the last case I'm going to look at, we have the two springs that are connected in series with one another. Okay, so what I want to do is I want to, again, compare the angular frequency and the period of oscillation of these three different cases. With the simple horizontal system with a single spring attached to a block M, what I've done is I've stretched the spring a distance x away from its equilibrium position. And what I want to do now is simply draw a free body diagram acting on the object when it's in this position. Okay? So let's start by labeling all the forces acting on the block. So the block has a weight. The magnitude of the weight is mg. We're going to assume that the block is resting on a surface, on a table. So there's also a normal force from the surface pushing up on the block. And now, since we've stretched the spring in one direction, we also have a force of the spring acting on the block. Okay, so we're not too worried about what's going to happen in this vertical component here, because those forces are simply going to cancel out. They're equal and opposite from each other. Let's look at what's going on in the horizontal direction. Now all we have to do is apply Newton's second law to this problem. Okay, Newton's second law says you add all those forces, and those are equal to mass times acceleration. So we have mass times acceleration is equal to the force of the spring. And in this specific case, the force of the spring is given by Hooke's law minus kx. Okay, I can just isolate the acceleration in this problem, minus kx, divided by the mass, and there we have it. Now, if you recall, the acceleration can also be written as the second derivative of the displacement with respect to time. That's equal to minus, again, k over m times the displacement. Okay, so this is our differential equation that we need to solve for this problem. So let's go over here. In order to solve this differential equation, you have to determine a function x that satisfies this equation. But you're in luck, I'm going to tell you what the answer is. X is some amplitude a, and now we need a time-dependent function. And for this specific case, for simple harmonic motion, you can use cos omega t, and you can also include a phase factor. Okay, now all we want to do is we want to substitute this solution inside this differential equation. So in order to do that, notice on this, this left-hand side, we have to take the second derivative of this function. So let's go ahead and do that. Okay? The second derivative of this solution that I gave you is simply going to be minus a omega squared, and again, times cos of the same function, omega t plus phi. There we have it. So now all we have to do is substitute everything back into our differential equation. One thing I want you to notice is, notice this term a and cos omega t in our acceleration. That's exactly what we have up here for our displacement. Okay? So let me just rewrite this as minus omega squared times x. This is really the acceleration of the system. Okay. Okay, so next thing we do is we simply substitute this back into the differential equation, and we're going to get that the left-hand side is minus omega squared times x is equal to minus k over m times the displacement. We can cancel the negative signs, not too worried about that. We notice we have a solution to this equation as long as omega equals the square root of k over m. Okay, if we have this condition satisfied, the solution that I gave you will satisfy this differential equation. Okay, and here's the angular frequency of this simple spring mass system. Okay, let's move on to the next case. Okay, I now want to consider the case where I have two springs connected in parallel to one another, as shown here in the top left figure. What I'm going to do is I'm going to apply a force F, and I'm going to stretch both of those springs some distance x. Okay? Now the goal of this system here, or the goal that we're going to have, is we want to try to replace both of these springs that are in parallel. And is there a way to rewrite the equations such that it looks like there's only one spring with an effective spring constant acting on the block? Okay, so I want to compare the left-hand case to the right-hand case. In both cases, I'm applying a force F in order to stretch the spring. In the left-hand case, I'm stretching two springs. In the right-hand case here, I'm stretching only the effective spring, and I'm stretching it by the same amount. So let's go ahead and look at all the forces acting on the system here. So here I have an applied force, and I have two forces pointing toward the left. I've got the force due to spring number 1, and I've got the force due to spring number 2. Okay? The magnitude is simply given by kx, and notice I have a different spring constant for each one of those forces. Okay. For the simple case, or the effective one, it's a little bit simpler because there's only one effective spring. I still have the force acting toward the right, and now I'm simply going to add the force due to this effective spring, and that force is going to be k effective multiplied by the displacement x. Okay, since the object is not moving, the sum of the forces should be equal to 0. So that means on the left-hand case, I have that the force applied has to be equal to k1x plus k2x. Okay? And in this case, I have to have that the force has to be equal to the effective spring constant times the displacement x. Now we can make these equal to each other. They both involve the force F, so we can eliminate the force F on the left-hand side of this equation and replace it with the effective spring constant times the displacement. And that has to be equal to everything else. K1 plus K2. Let me factor out the displacement here since it's the same on both terms. And what we get from this equation, if you have a look, that the effective spring constant for this parallel case simply equal to the, oh, it's getting a little bit messy. Let me try to rewrite it. Simply equal to the sum of the individual spring constants. Okay, that's great. So now if we go back to the original question was, what is the angular frequency of the oscillation? Well, now what you have to do is you simply remove the force F that was pulling this block, right? You just let it go, and I just want the system to vibrate. Well, this is a single spring with a single mass, and from the other side, the problem I just solved previously is the exact same problem, except in this case now I'm going to have K effective over the mass. And if you substitute the value of K effective, the frequency of oscillation in this case, once you've removed the force F and just let the system oscillate back and forth, it will oscillate at this frequency. Okay, so here's the angular frequency for the case where we have two springs with spring constants K1 and K2 in parallel with one another. Okay, now let's have a look at the case where I have these two springs that are in series with one another. So I've got the spring with spring constant K1 on the left, and then that's connected in series with a spring with K constant K2 that's attached to the block. And again, the goal will be to try to simplify this. And is there a way of rewriting the equation so I can represent this series, these two springs in series by one effective spring constant? Okay? And in order to do that, I'm going to proceed using kind of the same method I did in the previous case. I'm going to apply a force F to the block of mass m, and I'm going to end up stretching spring number 1 by some displacement x1. And then I'm also going to stretch spring number 2, and in this case the displacement or the stretching of spring number 2 can be a little bit different. It doesn't have to be the same. Okay. Now the one thing to consider about this top figure is that this is the applied force will be the same everywhere along the spring. The applied force is F over on this side of the block. It's going to be the same as on this side of the block. It's also going to be the same force that's applied between the springs here. Okay, so keep that in mind. Now in the bottom case for the effective spring, again, I'm just applying the same force, and my effective spring, I'm assuming that it's stretching some total distance x. And again, x can certainly be different from x1 and x2. Okay, so let's consider this system here. The one thing that we know from the top figure is the force has to be the same everywhere. It's kind of just a tensile system. x2, that there has to be equal to the force K1 x1. The object isn't moving. Well, I said 1, but I wrote 2. Let's try that again. Okay. How about in the effective spring mass system? What do we have? Well, in the effective spring mass system, we simply have that the force has to be equal to K effective. These K's don't always show up for whatever reason. Try that again. K effective and times the displacement x. Okay, so we've got two equations. The first one's representing the top system. The second equation represents the effective spring mass system. Now the one thing I want you to notice is that these displacements have to be linked to one another. Okay, the displacements of the individual springs in the top has to be equal to the full displacement or the full amount of stretch we get in the second case. So for this system in series, we have to have this plus x2. Okay, the next couple steps, we simply have to manipulate some of these equations. And I think the easiest thing to do for me is I'm going to eliminate all of the displacements here. That's really what I want to do at the end because I just want to get an expression that involves all the spring constants. So let's use the equation that links the displacements of the effective spring to the individual displacements of the individual springs. Okay, so for this case here, I'm going to use equation 2. Right, the second equation, I can eliminate the displacement, or the amount of stretch has to be equal to the force divided by K effective. I can eliminate the amount of stretch x1 using the fact that x1 has to be the force divided by the spring constant K1. And I can eliminate x2 using the same kind of argument. Okay. Notice we have that the force is in every single term. So at the end, I can simply get rid of it. Okay, so that means I'm going to have 1 over K effective has to be equal to 1 over K1 plus 1 over K2. Okay, great. I could take this one step further. K effective, if you put things on a common denominator, you're going to find is K1 multiplied times K2 divided by the sum. And the nice thing about having rewritten things in terms of one effective spring constant, because I know the frequency of oscillation of a system like this. This is what I solved in the first case. I know that the angular frequency of a simple system that has a single mass that's connected to a spring, the angular frequency is simply given by square root of K effective divided by the mass of the block. Okay, and in this particular case, K effective, simply multiply them. You have the mass in the denominator, then I have to add them up. Okay, and there we have it, folks. Here's the angular frequency for the spring mass system when I have two springs connected in series with one another. Okay, so let me recap what we just did for the horizontal spring systems. I've got a chart here I'm going to fill out. So the first case we looked at was one spring, one mass. The effective spring constant for that case, there was none. It's simply the value K. And now I'm going to assume in all of these cases, notice that in parallel and in series, I dropped the subscripts for 1 and 2, and I'm going to assume that all the springs are all the same kind, and they're all characterized with a spring constant K. Okay, so in this case over here, what you're going to have is that the effective spring constant is K1 plus K2. In this case, since the springs are the same, it's simply equal to 2K. Okay. How about in this case? Remember what we had, the formula was K over 2K. Okay, so I now just want to summarize what we did, and I'm going to compare the three cases, but I'm going to make all the spring constants the same. Okay, so the effective spring constant for the single one, just the value K. Remember, if I have two springs in parallel, the effective spring constant, I simply have to add them up. I get a value of 2K. And in this case, the effective spring constant, if you remember the formula, I had to multiply them in the numerator and divide that by adding them up in the denominator. Okay, so that would be K squared divided by 2K, or K over 2. Okay, now in each of these cases, the angular frequency was given by square root of spring constant divided by the mass. In this case, it's the same thing, except now the effective spring constant has to be used, so it's 2K divided by the mass. And in this case, it's simply going to be K divided by 2M, if the springs are the same. If you were asked now to compare the angular frequency, well, clearly the case where you have two springs connected in parallel will have the highest angular frequency, followed by the single spring, and followed by the two springs in series with one another. If you were asked to look at the period of oscillation, well, remember the period oscillation is connected to the angular frequency. It's simply 2 pi divided by t. Okay. So again, if I rewrite this now for this system, what I'm going to get is the period of oscillation for this guy, single spring mass is given by 2 pi times the square root of mass divided by the spring constant. Again, in this case, I'm going to get 2 pi. And again, it's the same term, it's just inverted. Over 2K. And again, the period of oscillation for the two springs in series with one another is 2m divided by k. Okay, so there you have it. I want to say a few things about the vertical spring system. Okay, I've sketched out 3 different cases here. The first one is I've just attached the spring to the ceiling and there's nothing attached to it. So it just has some natural length that I've written as x0. And in the second case, I'm going to attach a block of mass m to that spring, and I'll slowly let it down. And when it's in equilibrium, notice that we have some amount of stretching of that spring that I've listed as delta x. So let's consider this case here, because this is a little bit different from the previous case that we had for all the horizontal spring systems. We didn't have any initial stretching if there were no other forces acting on it. Okay, so let's consider all the forces acting on the object for the second case here. Okay, so the block is represented here by this free body diagram. So we have a weight acting down, and now since the spring is stretched a certain distance, we also have a spring force that's acting up, and the magnitude of that force is k delta x. Okay, now the system is in equilibrium, therefore those forces have to be equal and opposite to one another. K delta x must be equal to the weight of the object. Okay, and one last step, delta x must be equal to mg divided by the spring constant. So here's an important equation here. I notice if we have a spring that has a small spring constant, kind of a soft spring, you're going to have a large displacement, right? If we have a really stiff spring, so k is very, very big, the displacement's going to be very small. Okay, now what I want to do is I want to apply a force, and I'm going to stretch it out, and I'm going to let it go. Okay, and at some point it's going to start coming back, and I want to look at it when it's another distance x away from the previous case I just looked at. Okay, so let's look at all the forces acting down here. Now when the block is a certain distance x away from the case where it was in equilibrium. Okay, so for case 3, what I want to do is the same as before. I want to do a free body diagram. Again, we have the same weight as before. Okay, now we're going to have a spring force. Okay, the spring force, well, the magnitude of the spring force is going to be k. Now we have to figure out what displacement we have. Okay, we have an initial displacement delta x, which is there. And now we're looking at the system when it's kind of coming back, so there's another displacement, which I've written as x. That's the total displacement when the mass is over at this position. Okay, now we're going to apply Newton's second law to this system. I'm going to choose down as being my positive direction. Newton's second law says you simply add all the forces, and those have to be equal to mass times acceleration. So we have mass times acceleration must be equal to the sum of all the forces. So I've got the weight, mg, acting down, and minus the total force from the spring on the block. That's minus k delta x plus x. Okay, I'm going to simplify this a little bit more. I have mg. I'll carry out the multiplication here. Oops. Okay, k delta x minus kx. So notice this equation is a little bit different from the simple system we had for the horizontal spring system. However, if I go back and I look at the equilibrium position, remember what we had here. We had this equation when the system was in equilibrium. We had something linking the spring constant and that original displacement to the weight of the object. That's exactly what we have right here. Those two terms cancel out. They are equal to each other. The weight is actually equal to k delta x. Therefore, we can cancel those out. And what are we left with? Well, I could just rewrite this Just give myself a little bit more space here. We have that the mass times the acceleration is simply equal to minus kx. This equation should look familiar to you. It's the exact same equation we had for the horizontal spring system. Same as horizontal. Okay. So if we have the same differential equation, we're also going to have the same angular frequency. Okay. So we could substitute the trial solution that I gave you for the displacement and go through all the math again, but we really don't have to because we've already done it. We already know that the angular frequency for this case is simply going to be the spring constant divided by the mass. It's exactly the same as what we had for the horizontal spring system. The only difference is that my equilibrium position is not the natural length of the spring. Okay? Whereas for the horizontal spring system, the equilibrium position is basically the natural length of the spring. Okay, the last thing I just want to say about this spring system is, well, we've got our equation for the angular frequency. We found it was the square root of the spring constant divided by the mass. So what happens though when the mass equals to 0? Right? What if I don't attach a mass to that system, but I still stretch the spring and I kind of let it go? We see that there's a problem here. Right? If I set the mass equals to 0, if mass equals to 0, if there is no mass attached to the spring, I'm going to get an angular frequency that is very, very big. And physically, that doesn't make a lot of sense to me. So next time what I'm going to do is I'm going to kind of correct this problem. Because everything that we've done so far is we've assumed that all of these springs don't have any mass. So next time what I'm going to do is I'm going to actually consider a real mass or a real spring that actually has a weight. Okay, so stay tuned for that.